right, so for today we are looking at quadratic functions and transformations. And essentially quadratic functions and transformations are going to be a new set of equations in which we are graphing parabolas. You are going to see this new set of equations as similar to an absolute value, but different in various ways. So what we're going to do today is investigate some vocabulary. We're going to really look at how they relate back to the absolute values that we focused on in previous chapters. So go ahead, take a minute, and identify the coordinates of the vertex for each of the following absolute value graphs. So, in example number 1, your vertex was 0, 0. A vertex of 0, 0 and a slope of 1, 1 makes this what we call the parent function. The equation of this function is simply the absolute value of x. In example number 2, your x value is 0, but your y value is 3. So my vertex is 0, 3. This graph is also reflected. So when I write its equation, it's a negative absolute value of x, and then the plus 3 for the movement up 3 units. And number 3, it goes 1, 2 units to the right. So that makes my vertex 2. And it goes down 3, so negative 3. It still has a slope of 1, 1. So this has an equation of y equals absolute value. It's x minus, and then your h value, and then your k. So hopefully all of that comes back to you. You kind of remember doing something like this in chapter 2. I know it's been a while. We did it a little bit in chapter 3 with graphing and shading. So what we're going to do today is extend upon our knowledge about the vertex of an absolute value and use it to apply that same information to a quadratic. So we have the parabola of a quadratic function forms a parabolic shape. So a parabola of a quadratic function forms a parabolic shape. So absolute values made u, absolute values made v's, quadratics make u. Quadratic functions have two forms to their equation. Just like a linear function, they have standard form with ax squared plus bx plus c. And similar to an absolute value, they have vertex form, where you have a parentheses x minus h parentheses squared plus k. We have two rules. A cannot be 0. Just like an absolute value, we have a line that cuts that graph in half. The line of an absolute value and the line of a quadratic have the same name, and that name is the axis of symmetry. The axis of symmetry. The equation takes on the same form. It is x equals h where h is our vertex coordinate value. The vertex of the parabola is its min or max. So again, the vertex of the parabola is the min or max. It's also the point where the axis of symmetry crosses. It is a coordinate. Its coordinates are HK. We can graph the absolute or the parent function for a quadratic. That is y equals x squared. That represents the parent function. You can see here that this point is the vertex. I placed it in the middle. And if you notice, the points going to the left are negative. The points going to the right on x are positive. And the y values repeat. So when x is 1 or negative 1, y is 1. 2 or negative 2, 4, 3 or negative 3, 9. So we would say that this graph is a function, but it fails the horizontal line test. Therefore, it is not one-to-one. So it is a function, but it is not one-to-one. We talk about the parent function of functions a lot. So the parent function of a linear function is y equals x. The parent function of absolute value is y equals absolute value x. The parent function of a quadratic is y equals x squared. The parent function of a quadratic is y equals x squared. So we have our parent function. Its axis of symmetry is x equals 0. Its vertex is 0, 0. And just like linear and absolute value functions, the domain of a quadratic is all reals. The domain of a quadratic is all reals. And our range relates to our vertex's k value. So in this case, the range is greater than or equal to 0. If my graph was reflected, it would be less than or equal to. And that's what we're going to talk about next. So just like absolute values, we're going to talk about what does the a value of a quadratic do to its graph. What does the a value of a quadratic do to its graph? So how we graph quadratics is starting with the vertex. We're always going to graph the vertex. Then we're going to graph our points to the right of the vertex. And then we're going to use symmetry to pass the points to the left. And then we're going to connect our curve. And that is what is new about quadratics. This is a curve. You do not want it to look linear, then you would be graphing an absolute value. So you need to make sure when you connect this that it has a smooth curveness to it. So we want to graph a function of the form f of x equals 1/2 x squared. So just like previously, a 1/2 of an a value is going to compress my graph. So a values between 0 and 1 compress our graphs. A values greater than 1 will stretch our graphs. So again, the same as the rules for an absolute value. Our vertex in this case is 0, 0 because there is no transformed h or k. So I can plot 0, 0 on my graph. And then I'm going to make a quick table to the right of my vertex. So I'm going to plug in 1. 1 squared times 1/2 is 1/2. 2 squared times 1/2 is 2. And 3 squared times 1/2 is 4.5. It's important to note, a lot of times when we first start looking at these, students try to take 2 times 1/2 first and get 1 and then square it. Order of operations are PEMDAS, which means you have to do the parentheses or the exponents before you multiply or divide. So you cannot multiply this number in x before you square it. So your first step is to square that x value and then multiply. On my graph right here to the right, what I did was in black, I drew the parent function, and then I graphed 1/2 x squared, which is my compressed graph, in green. So you could see how the green graph is wider than its parent function. So a compressed function will be wider than its parent, and then you are able to see that graphically. The graph or line of symmetry is the AOS. It is the y-axis in this case, or x equals 0. It is the x-coordinate of the vertex that we set that equal to. So what do you predict will happen if the graph of the function ax squared is a negative a value? So what happened if we had a negative a value for an absolute value? What will happen if we have a negative a value for a quadratic? A negative a value is going to cause my graph to open down like a frown. So if the value of a is negative, it will reflect across the x-axis. So just like in the past, if a is positive, it opens up. It looks like a smile. If a is negative, it opens down like a frown. So your negative, sad face, and your positive, happy face. And the last thing I want to talk about today is that reflection. So if a graph is reflected, then it's going to change the direction it is opening. So if we have a negative a value, then it's reflected across the x-axis and open down. If a is greater than 0, meaning positive, then my parabola has what we call a minimum and opens up. So when the a value is positive, it opens up and has a min. That's this first example here. If my a value is negative, it opens down and has a max. That's the second example. And then in our first graph, we looked at an example of compression. Compression makes my graph wider. A compressed graph will have an a value between 0 and 1. An a value greater than 1 stretches my graph vertically, making it narrow. A value greater than 1 stretches it vertically, making it narrow. So for tonight, you're doing those next 2 pages in the packet. You are doing 5-1 day 1 and the 5-1 day 1 continuation on the back where you're finding the vertexes of those graphs. For the 5-1 day 1, make sure you list the transformations. Make sure you list the transformations on that front page.